Okay, so we're going to talk about eigenvalues and eigenvectors. Pretty straightforward. If A is an n by n matrix such that AV equals lambda V, then we call lambda an eigenvalue and V lambda an eigenvector. Okay, let's look at an example. Suppose I have this matrix A and this vector V, 5, 2. If I multiply them together, I get 10, 4. And 10, 4 is a multiple of 5, 2. So we get 2 times 5, 2. So we now have the lambda is equal to 2 as the eigenvalue, and the eigenvector is 5, 2. Actually, it's going to be any multiple of 5, 2, but 5, 2 is what we have. Okay, so let's see how to actually find one of these suckers. What we're solving for is we want to know when AV is equal to lambda V. So solving, bringing this over, I get AV minus lambda V. I'm going to suck out the V. But notice if I suck out the V and leave just the lambda, that doesn't make sense. You can't say a matrix minus a number. So we have the identity matrix in there as a placeholder. So we're looking for solving this equation or systems of equations. Now, we know that if the vector v is 0, this has a solution. We always have a solution, the trivial solution for anything equal to 0. What we're looking for is the non-trivial solutions. And the only time that happens is when the determinant of this thing is equal to 0, when we have a singular matrix. So that's what we're going to be looking for. We want to look for when the determinant of a minus lambda I is equal to 0. You will get a polynomial when you do this, and it's called the characteristic polynomial. Okay, let's look at an example. Let's say I have this matrix. We're going to look for the eigenvalues and the eigenvectors. So using Maple, I will set up the matrix, let A equal all that crap, type it all in. I need the identity matrix, so I need a 3 by 3 identity matrix. The easiest way to do that is to use DAG 1, 1, 1, because there's only ones down the diagonal. So I need to look at A minus lambda I3. So I have evalim A minus lambda I3. So notice how I have like negative, why did I put them in the front? That's weird. We have negative lambdas down the diagonal. So now we find the determinant of that. Ping, love Maple, love, love, love Maple. And of course, now the next thing I have to do is factor that. What a pain in the ass. But we can use Maple again and say, factor it. Now, hopefully you can look at this and see that the eigenvalues are 5 and negative 3, but in case you can't, you can always say solve the above thing for lambda. So we have 2 eigenvalues. We've got 5 and we've got negative 3. This is listed twice because the multiplicity is 2. Now we have the eigenvalues. We need to find the eigenvectors. So we're going to go back and plug our lambdas into this guy and then solve that system of equations. So first looking at lambda equal negative 3. We plug that in, lambda 3, so we get this matrix. I roof it. I get this when I solve it. So when I solve this, notice I have 1 pivot, 2 free variables. Solve it just like we solved it before. Sorry, this is kind of a mess. I try to write with my mouse. So we're going to let z equal s. We're going to let y equal t, which forces x to be negative 2t plus 3s. Putting that into a vector like that, then we separate the s's from the t's. So the 2 eigenvectors are negative 2, 1, 0 and 3, 0, 1. A lot of times, not always, a lot of times, if the multiplicity of your eigenvalue is 2, you will get 2 vectors. We like when we get the number of vectors equal to the number of the multiplicity, but that's for another day. Okay, now we've got one more. Let's look at 5. If lambda equals 5, we plug that in, we roof it, and we get this matrix. Notice now I only have 1 free variable. I will let z equal s, y is equal to negative 2s, and x is equal to negative s. So reading up to get my x, y, z, sucking out the s, I get negative 1, negative 2, and a 1. So the eigenvector for this matrix, for this value is negative 1, 2, 1. And that's how you find eigenvalues and eigenvectors. Now we're going to start doing it in class.